Welcome to week 5. As we finish up chapter 12, talking about the solutions and colloids and things like that. So today's lesson will be the last little part of chapter 12. We're going to be talking about soaps and detergents. So trying to find the exact spot here. So we're on page 220. On page 220, soaps and detergents. When a few lessons ago we were talking about how likes dissolve likes and things that aren't similar don't dissolve. So if you have something that has polarities, like water has a polarity to it, then it will dissolve things that have polarities quite easily. It'll break up things like salts. It dissolves things that can have that type of thing, and they will. But if you have things that don't have a polarity, something like hydrocarbons or oils, they will tend to keep separate from themselves. And so what a soap does is at the top of the page on 220, there's a molecule drawn there that is a soap molecule. And if you look at it on the far left, there is a little spot there that has a positive ion attached to it. And the whole soap molecule is non-polar, except for the little tail on the end is polar, which gives soaps this really interesting ability. The soaps have the ability to kind of break down this barrier between polarities and non-polar type items. So a soap is either a sodium or a potassium salt of some kind of fatty acid. That's what a soap actually is. There are stearic acids and things like that. That's what's shown on figure 1220 that's at the top. And it's a sodium stearate. So that positive ion is a sodium ion that's attached to it. And so if you look at the lower part of the page, there's a picture that shows a sink where water's being poured in and you're getting the bubbles because it's soapy water. And then down below that is a picture that shows water with oil droplets. And there's little red droplets that are in there. And because the one end of this soap is non-polar, it will mix into the oils. But then because the other end of it is polar, it leaves the polar side floating around, and that's what those little red dots you're seeing. You're seeing the end of the soap out there with the polar end, and it will connect with the water. And that causes an emulsification where they will intermix with each other, and it allows droplets of oil to be able to be surrounded by water and not just completely separate. And that's why when you put soap on your dishes or things like that, that you can get the oils to come off, because the soap will get in there with the water and emulsify with the oils and allow the water to then mix with the oil and carry it away. Otherwise, the water and the oil don't really mix and you don't get that. Now, one thing with soaps though, a standard soap, is that it is insoluble in hard water. The hard water, the calciums and the things that are in there, make it so that it leaves a hard scum from the soap. And that's why detergents were made. In fact, to be fair, almost all soaps, even bar soaps that you use from the store that are modern soaps, are actually detergents. because detergents are not affected by hard water the same way. And on the bottom of page 220 is a picture of a sodium lauryl sulfate, which is a detergent. Now, some people have issues with some of these and they are bigger, heavier chemicals. Some people's skin react with them and things, but that is the purpose of a detergent, is that it has similar characteristics to a soap. As you look there, you can see on the end that there still is a sodium ion on the end. That's why it's the sodium lauryl sulfate. But it has this big long chain that is nonpolar, and so it will do the same thing. It will get in there and it will emulsify and create these things that cause it to help break up the oils. Now, just below that is a sorbiton monolaurate, which is another one. They're just different chains. They're bigger, they're longer. Now, in your body, this kind of stuff is going on as well. When your body digests heavy, fatty, oily foods, then you have things like bile and things like that that get in there, and they help to emulsify those oils so that it breaks it into smaller particles and your body can use it. If it wasn't for that, these oils would remain larger and clumped up, and they wouldn't be as easy for your body to actually get the water in around it and make it usable. So this kind of stuff happens not just in soaps, but in your digestion system and things like that. So that kind of finishes chapter 12. And what we're going to finish the rest of this particular lesson on is we're going to do a review now of chapters 11 and 12. And we're going to go through each, kind of over each part, and we're going to do a complete review. And so I will not have a video for tomorrow's lesson. This week we'll just have 2 videos. But tomorrow's lesson, I will be giving, turning in the tests so that you can pick them up on Monday. And then for your second part of this week's set of lessons, you will be doing the test, and it will be on chapters 11 and 12. It's on one piece of paper, but don't forget to turn it over, because the second half of the test is on the back side. It's a total of 25 questions. Second of all, don't forget to put your name on the top. By putting your name on the top, then that way I can give you credit for it. That's really important. In fact, just like with every other test, on this one, I think it's even more important with the way we're doing it. If you put your name on the top, you'll get a point, just as if it was one of the questions, just to make sure we get that and don't have any issues with not being able to know who turned in what. So starting with the review, we're going to go back and talk about, in chapter 11, we were talking about metals and semi-metals and some of their characteristics. If you look over here at the periodic table, everything on this side, on the left side of the chart over here, is a metal. And in your back of your book, there's the periodic table. And there's a kind of a kitty corner line over on the far side. I guess that's not really showing up in my image very well. But when you get over to boron and down along there, there's that line in your book that has the periodic table. And I'm even going to adjust this just a little bit, see if I can. Yeah, there you go. So you see this line right here, that everything over here is a metal, and everything over there is a non-metal. Now there's a lot more metals than there are non-metals. Let's talk a little bit about some of the characteristics. So a metal, it conducts electricity, usually, quite well. It conducts heat for very similar reasons. It's malleable. You can work it with a hammer and bend it and things like that. It's usually bright and shiny. So those are some characteristics of metals. They're usually quite tough. Semi-metals which are getting close but aren't quite into the nonmetals, have some of those same characteristics, but they start to have a few of these other things where, because a nonmetal is usually dull, doesn't have much of a luster, it's brittle, it doesn't conduct electricity very well, if at all. Semi-metals are able to have some really unique characteristics, which we'll probably talk a little bit more as we get farther down, but such as like semiconductors that are based on silicon, which is right on in the middle of those semi-metals right there, the Si, it's right on that border, and it has the ability to conduct really well in one circumstance and not conduct at all in another, and that's why it's able to be an electronic switch in a computer, which everything that we do pretty much now is based on. This video is being recorded. Your video you were watching, the screen, all the information is using these transistor semiconductor switches. So, let's think about next thing. What is an alloy? So, an alloy is where you have a mixture of metals that aren't necessarily bonded into a molecule, such as H2O is a molecule, and they're not bonded like that. An alloy is where you have mostly a pure metal, say, and then you have some parts of others that are in there as a mixture, but it's in metal. So, for instance, brass. Brass is a mixture of copper and zinc. It still has a really unique characteristics. It's strong, it's malleable, it has a shiny luster, it has all of those features, but many times an alloy can have more important or at least different characteristics than the original. So brass is quite strong and has some really cool characteristics. Not so much anymore, but a lot of old fixtures and knobs and things like that would be made out of brass. Some things still are. It can tarnish and turn kind of a discoloration, but it can be repolished. Things like brass that's used, in fact it's even called brass a lot of times for the shells that hold the powder for like gunpowders and things like that. Another alloy would be bronze, which is copper and tin. Has a lot stronger characteristics than just copper. And it has some really cool characteristics. And it's that mixture, mostly copper again, but with a fair amount of tin. And earlier we've talked about the percentages and stuff like that. So that gives you an idea of what an alloy is. There's also like steel alloys, because we have iron that we've talked about, but steel is when you start to add other parts into it to create a mixture that creates things like stainless steel or carbon steel and those kinds of things like that. So, alkali metals, which are these first ones here. And the most abundant of the alkali metals that are on Earth are sodium and potassium. They're fairly abundant. Let's see. One of the things that we talked about also in chapter 11 was cement and the making of concrete and cement. And that's a mixture of limestone that is heated up and clay mixed together, heated up, and into a mixture with water and gravel and stuff like that. And that creates the concrete. And then the method that we use to get iron, to get iron from the ores, the iron oxides and things like that, and turn it into iron ore, we talked quite heavily about that and the blast furnaces that are used, and I drew the designs and stuff like that. It's a blast furnace that's used to get cast iron, which has a fairly high carbon content in it because of the way it's made and that. And in order to get quality steels, you have to process it and purify it a little bit to get that carbon to get to lower levels, and then you have those other alloys in to get things like molybdenum steel or vanadium steel or stainless steel and all kinds of different kinds of steels. Mild steels, hardened steels. Sorry, most of this, when I would be doing this face to face, I would be asking you these questions and then asking you to try to give me the answers to these. But so what is the process called where we heat metal up and then harden it? Like a blacksmith, he heats up a knife and he pounds it and shapes it and gets it really, really hot, and then he dumps it in oil. That's called quenching, and that causes there to help it to become quite, it increases how brittle it is depending on how fast it is quenched, but it causes everything to shrink and to force it into a hardened position. And it makes it so that you can have something like a metal that will then hold a sharp edge for a long period of time. If it's just mild steel, you can sharpen it and it just dings, and even just trying to just cut things, it's soft enough that it loses its sharp edge. And the tempering process that goes along with that is after you quench it, if it's too brittle, there are processes where you heat it not quite as hot, but you get it fairly hot and then allow it to cool slowly, and that'll bring it back from that brittleness but still leave a lot of the hardness, and so that's tempering. And I talked to you just a few minutes ago about what the alloys were that make up brass and what the alloys are that make up bronze. So brass is copper and zinc, and bronze is copper and tin. So of all the metals on Earth, what metal is the most malleable, the easiest to shape? And that would be gold. In fact, it's so malleable and poundable and shapeable that it can be pounded almost thin enough to be one atom thin. Or just a couple atoms thin. It can be pounded so thin, much, much thinner than a piece of paper. Super, super thin. And nothing else like even gets close to that. By the time you start getting that thin, it still starts to get brittle and gets work hardened. If you take a piece of wire and you flex it back and forth, it'll bend the first few times, but pretty soon you've bent it enough that it gets work hardened, and that work hardening, it gets brittle and it breaks. Gold has the ability to do much more of that than pretty much about anything else. The two elements that conduct electricity better than any other elements are copper and silver. Now, some others conduct electricity really, really well, and they still have their advantages for certain things. Because gold doesn't tarnish, sometimes even though it doesn't conduct electricity quite as well as silver does, but it doesn't tarnish, and so there are times when those will be used. But why would you think we don't use silver then for wires if it conducts electricity so well? Probably because it's so expensive. I mean, could you imagine? It's much, much, much more expensive. Copper is even very expensive in today's markets, but it's still a fraction of what silver would be. And we talked about how aluminum conducts electricity actually quite well, but because it tarnishes and its oxidation is non-conductive, it's extremely dangerous if not processed properly. Back in the late 60s, early 70s, there was a lot of building that was going on, and they were trying to use aluminum in house wiring inside the house. And that's really dangerous because the aluminum oxides don't conduct, then they get hot and you get house fires and all kinds of stuff. So, I don't know if you can remember, we talked about this, but there's a specific metal that's used in catalytic converters in automobiles to try to help with pollution control. And it's mostly a catalyst that helps to cause the reburning or superheating of the materials so that they fully combust. That metal would be platinum, which is very expensive metal. Catalytic converters on automobiles are quite expensive. Let's talk about what metals are the most prevalent on the Earth's crust. So iron is really high. It's the first. The second most prevalent is aluminum. No, sorry. Aluminum's the most. Iron is the second, but it's used more than aluminum because it's easier to process originally. So sorry, aluminum is one of the most abundant. So why would aluminum be used so much in the aircraft industry or space launch? And the answer to that is that it has a very light weight for its strength, so it has a low density. And then there's another thing is, on the Utah State Capitol building, the dome is covered in copper. And the Statue of Liberty is covered in copper. And many times you'll find raw aluminum pieces that are used for decorating things like railings and things like that. And why are they resistant to corrosion, I guess is what I'm trying to ask. And the answer to that is that when they do oxidize, which they do, the copper turns kind of that dark green color, aluminum gets kind of a white, aluminum oxide, the copper oxides gets dark green. But what happens is that the oxidation that happens is a hard oxidation. So, and it's bonded to the copper. So copper oxide does not separate from the original copper. I don't know if you've ever seen an old automobile driving along and you can see the rust that's eaten through, and some people will call it that car has cancer and things like that. Well, why that happens is that when iron rusts or oxidizes, which is what the rust is, it's flaky and it pulls away from the original material, then exposing raw iron to then reoxidize. And things like copper and that don't do that, and so they last a much, much longer. It's not that it doesn't ever come free at all, or there isn't some drawbacks and over time eventually it needs to be replaced, but it can be there for 100 years or so where iron that's exposed like that would rot really fast. So, in today's economy, what's the main use for lead? And that would be mostly for batteries and also used in nuclear power plants and for shielding for things like x-rays and things like that. So when you go to the dentist, they're going to take an x-ray of you and they put the shield over you. Inside that shield that they put over you usually has lead sheets and things like that because it's a really dense material and it helps to reduce the ability of radiation to get through it. That's also some of the reasons why it's used in nuclear power plants, but it's also used in the rods, they have a big chunk of nuclear material, which we'll get more into in later chapters, and they will slide cadmium rods and lead rods for different purposes, but the purpose of the lead rods is to block some of the radiation. The cadmium has some other stuff we'll talk about later, but that's the main use for lead. And now these aren't necessarily metals, but the first and second most abundant elements on the entire Earth crust. This is with all of them, not including just metals. And the most abundant is oxygen on the crust, and the second most is silicon. Because almost all of your rocks and sands have silicon in them. The sand is a silica base. And oxygen, when you think about it, it's part of all the water. As far as by mass, it's very heavy. It's by far the most heavy part of water when we think of all the oceans. And also there's a lot of oxides, different kinds of oxide metals and everything. So oxygen is the most prevalent and silicon is the second most. And obviously we know one of the main uses for oxygen is we breathe it. And all living things, it's important. One of the main uses for silicon is the computer chip, which we already talked about. We talked a little bit in chapter 11 about asbestos and its use as a fire-resistant material. It's not used as much today as it used to be. There still are cases though where it is really important. They used to put it in things like the ceiling, popcorn in the ceiling and stuff like that. And it's really bad stuff, and it has really fine fibers that can get into your lungs and really mess you up. But that's one of the main purposes that asbestos is used for. Let's see. Let's go into chapter 12. So in chapter 12, which is the one chapter we just finished, was talking about solutions and colloids and things like that. So think about the solutioning, and you have your solute and you have your solvent. And the solvent is the material, like for instance, if you have a glass of water and you put some salt in there and mix it up, the solvent would be the water and the solute would be the salt that gets mixed up and totally goes into solution. It doesn't, you could pour it right through a filter and the salt would go right through it. It's not big chunks or anything like that. If something is miscible, then it would be completely soluble in each other. So salt can be completely soluble in water, and that means it's miscible. What are some ways that you can make something dissolve more quickly? Sometimes you may have seen something in water and it's not completely dissolved. And the answers to that would be one, to stir it. Maybe if you stir something, I don't know if you've ever mixed something like powdered drink in water, and if you stir it, it will mix faster. Or you can crush the particles to make them smaller. That makes it easier, because if you have a big chunk of solid salt, you may be stirring for a long time. You break it into little pieces, it'll dissolve faster. Another way of doing it is to increase the temperature, because then the molecules are moving faster and they will mix quicker. Earlier in this lesson, we were talking about soaps and detergents and the fact that likes dissolve likes. So water, which is polar, is able to mix with things that are polar more easily, and things like oils and things will mix with things that are non-polar. So, and if they're if they aren't like, then they don't like to mix. So. What does it mean when something is saturated? So if we were to say that water was fully saturated with sodium chloride at a specific temperature, because temperature can affect what point that saturation takes place. And what saturation means is that you put so much salt into the water that it can't dissolve anymore. It's dissolve all it can. And at that point, it's fully saturated. It cannot accept any more into it. And it would be at equilibrium at that point if it's fully dissolved and nothing else is in there. Now, the stuff in it, if you have more puddled salt on the bottom and it's fully saturated, you would have a situation of equilibrium going on where some of it would still be dissolving and some of it would be recrystallizing, and you'd have that process going back and forth. And it would be in a state of equilibrium at that point. The next thing would be, how is solubility affected by pressure? So I don't know how many of you did, because so far I haven't had anybody turn in any lab information that they did, because I mentioned that if you did a lab on the soda pop and the Mentos, that I would give you some credit for that. But that is a super saturated material or liquid, but it was under pressure and it can hold more under pressure. When you pop the lid, it releases some of that gas almost immediately because you've released some of that pressure. So when it has more pressure on it, a liquid could hold more gas in it. But pressure doesn't increase the ability of solids or liquids themselves. So a liquid in a liquid or a liquid in a solid, pressure doesn't affect them very much, but it does affect gases, particularly in liquids and to some extent in solids. How would temperature affect the ability of something, its solubility? So temperature will increase the solubility of liquids and solids, but it doesn't affect gases that much. So if you have gases that are all intermixed, like air is actually a solution of air that's a mixture of oxygen and carbon dioxide and nitrogen and a little bit of argon, and these things are all floating around in there, and the pressure change really doesn't affect how much there is of which one. Or even temperature doesn't really affect how much. The temperature doesn't affect how much is. If it's hotter, you still have 21% oxygen in the air. If it's really cold, you still have 21% oxygen in the air. But temperature will affect how much liquids and stuff like that will. So we talked about in the earlier, one of the questions that was asked, if temperature is cooler, it can hold more gas, and if it's hot, it won't be able to hold as much gas because they'll be moving around. The gas will be kicked out. So one of the questions that you had on one of the previous things that we asked you to turn in for some of the review questions was talking about cold water in the ocean. And why does cold parts of the ocean seem to actually have more living life going on than really hot parts of the ocean? And that's because the ocean, when it's cooler, can carry more oxygen. Let's talk a little bit about molarity. So there's two types of molarity. One is a capital M. We denote it with a capital M, and that means the number of moles per liter of solution. So if it's a capital M, it's the number of moles per liter of solution. And then there's molarity with a little m, and that would be number of moles per kilogram of solution. So, which car alarm's going on? That's great. The vapor pressure of a liquid. So, we talked about the vapor pressure of a liquid, and that's the amount of pressure that it has and its desire for molecules. Like if you have water sitting there on the table overnight and you go in the morning, there'll be less of it because some of it is going to leave into the air. And that vapor pressure at the certain amount of atmospheric, and that is that vapor pressure. It's the pressure exerted by vapor when it's in the liquid, when it's at equilibrium, where you're not really losing that much and that's equilibrium, that's the vapor pressure. If you put it under more pressure, it can hold more vapor within it. And temperature will increase the vapor pressure. So if I take a pot and stick it on the stove and turn the heat up, when it first starts, it's cold water. And there's a certain amount of vapor pressure, which would be its standard atmospheric vapor pressure, and it would just be sitting there. And that's why it's a liquid, it doesn't just immediately evaporate. Where if you take something like alcohol and you pour a little bit of alcohol on a table and just a little bit of water on the table, the water's going to sit there for quite a while before it evaporates. The alcohol has a higher vapor pressure, and it'll immediately, or more quickly vaporize and turn into a gas. But as the pot of water that's on the stove starts to heat, it'll get hotter and hotter, and pretty soon those electrons are moving around, particularly right on the surface. They're moving around, and eventually one of them's moving towards the surface. It just leaves the water and it's gone, and then so it's floating around in the air above it. And the higher the temperature is, the more of that's happening, and that means it has more pressure, more desire to leave the liquid. Let's talk a little bit about electrolytes now. This is the next one. You've probably heard of electrolyte drinks. Basically, they're ions, usually some kind of sodium or potassium ions, and that they're talking about as far as drinks go. But electrolytes is just an ion that helps something conduct electricity. That's what an electrolyte is. And so in your body, if you don't have enough electrolytes, it'll cause muscle cramping and things like that, because what causes your muscles to function and work properly is the fact that there are electrolytes in your system, so those electrical signals do what they need to do. Osmosis, that was another thing we talked about. So osmosis can occur anytime that there is a difference in concentration of solution on two sides of a semi-permeable membrane. So you have a membrane in the middle, and you have a solution here and a solution here, and they have different concentrations of that solution. And if you have seawater on one side and pure water on the other side, the liquid will move, the pure water will move through this solution, and the flow is naturally from the more diluted solution to the more concentrated solution. So water is going to constantly move through into the more concentrated solution. Now, in the world today, that you can set up when you create certain pressures and everything else, and you can force what's called reverse osmosis. And in today's world, that's really important, especially in places that don't have very much good drinking water and they live near the ocean, because the ocean is very salty. And places like Saudi Arabia, where they have lots of oil money but not hardly any water, they set up these special plants, and they'll take seawater and they will do a reverse osmosis process where they will force osmosis in the reverse direction, and they get pure water. And so it's quite important. And so let's talk about we've been talking about solutions and stuff. Let's talk about a little bit about colloids and what's the difference between a solution and a colloid. So a solution is a homogeneous mixture. It's evenly mixed and it's fully and completely mixed. But a colloid is a heterogeneous, tiny particles where you'll have a clump that is not fully incorporated, but it's small enough that it still is distributed within the water or whatever. Such as a smoke particle that's floating through the sky will kind of cloud the sun. We talked about those kinds of things. It's too big to be truly part of the solution of the air. And that would be particulates and things like that. Smoke particle may be a little too big to truly be a colloid, but we'll get into that a little bit more here in just a minute. But the colloids are just too big to be truly fully solution, but they still can be suspended within the material. When you have absorption, it's the attraction of a substance to the surface of a solid, and I'm not too worried about that one. Here again, earlier in today's lesson, why is soapy water more easily able to clean things than just pure water? And that's because it has the two tails, one that's non-polar and one side that is polar, and so it can play and emulsify and work with both. It has the both abilities. So we were talking about vapor pressure just a minute ago, and if I was to add something like sugar to water, would it increase or decrease its vapor pressure? And of course, the correct answer to that is it would decrease the pressure, because as it gets into solution, the sugar is there and it along in that surface, and so there's less surface area that's pure water, and that less surface area means that it has less desire and pressure to leave. And it doesn't matter whether it's sugar or salt or any of those kinds of things. If they're doing the same thing, they're going to cause that reduction. Alrighty. I think that pretty much, we'll call that the end of the basic review. I think that'll probably pretty well allow you to get most of the ideas of what would be necessary to answer the questions on chapter 12, 11, and 12. So tomorrow's lesson will be do the test, so there will not be a video for that. And then the third lesson of the week, we will start chapter 15. Now we're going to jump a couple of chapters here. I did that every time I teach this class because there's actually more chapters here than we have time to get through in a given school year as it is. And so we'll be jumping to chapter 15 and kind of spend a little bit of time in that one starting on the next video. Thank you.